Hi, I'm Anthony Zalata, and I'm doing my extra credit lecture on 15.2 line integrals. Part A. For Anthony. No, because my partner is going to do the second part. So, let's begin, shall we? So, line integrals, what are they for? Well, some people use them to find different things. Today, in this lecture, I'm going to show you how to find mass. And to use a line integral, it has to be in a smooth line curve. And the only thing that has mass in a smooth line curve, or one of the only things, is a wire. So that's what we're going to be finding the mass of today. So first we start with a three-dimensional space. And then we start making points and we get our wire. Alright, looks like a good wire. So this is point naught, it's point n, number of points. And then these are some arbitrary points here. And we're going to use I to be the index, so however many points. And this one's however many points minus 1. So then this would be the distance on which the changes in the density. And that's how we're going to find the mass, because the density isn't always constant. And the density is represented by rho. I'll write it over here so it's better. It's represented by rho, and it equals a function of x, y, and z. So we could use these things to approximate mass. And it looks something like this. See this, what it is basically is the distance here and the change, the amount of change times the rho, all summed up in their different parts. Boom, 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 along the smooth curve of the wire. This will give you a good approximation of the mass. But since we're in calculus, we don't like approximations, we like exact numbers. And to get exact numbers, we need derivatives. So we're going to start with ds here. And the ds is the change, but basically the derivative. And then we know it equals the magnitude of the vector valued function's derivative. And we could write it like so. And that equals this. And it is in terms of t, so we got to also write that there. So let's put it here. Okay, if you can't tell, that's supposed to be z prime of t squared, but kind of looks a little jangled up there. But that is basically what ds equals. And then this is fine, but it has to be in terms of t because we have this. and you get your vector valued function instead of to get the direction and change in distance. So we use our vector valued function in the form of this. That's supposed to be okay. There we go. And then so that's how you get these numbers here, and then this formula. And then we plug it in here because we have to make it in terms of t. So when you get your function and your vector value function in the form of a magnitude and primed, you get it looking like an integral, which is very familiar in calculus, and it looks like this. You also start from a point on the wire, and it would be the t is within that space. Don't forget your dt. And then that's your formula you'd use to find the exact mass of that wire. And that's what calculus line integral is about. So now I'm going to show you an example over here to show you how to evaluate a line integral. And we're going to start with an example from the notes that we learned in class. Alright, so we got to evaluate our line integral 2x, y, z ds. And this, our c is given by the vector valued function here, t, 2t, 2t. And it is between the values of 0 and 1. So let's evaluate this one here. Let's start by first getting the prime of the vector valued function, and then we'll go to the magnitude of it. Alright, let's take the magnitude. Alright, there we go. We got our magnitude of vector r prime t here. And then now we need our function in the terms of t, because Now we're doing it in the terms of t. So it would look something like this. Now all we have to do is put it under an integral and evaluate it. This simplifies to this, by the way. So then we can do our line integral and find the mass of this thing, of this wire. And this is a real simple one, so it turns out to be 24t cubed here from 0 to 1 dt, and that equals 6d right there, evaluated from 0 to 1, and that equals 6. And that is your answer. So this would basically be the mass of the object when you go along and add up all the individual pieces. And the density is very simple in this one. It just basically gets bigger the more dense it is, the farther along the wire. And it's doesn't have any crazy things going on in there, so it's quite simple. But basically it gets harder when you get things like crazy square roots and whatnot, and you get to end up looking like their squid or octopus buddy here, and he looks a little bit like this. As you can see, he was not having a good time later on in Calculus 3. He knows it's coming. And he's like, get me out of here, man. I don't know. Anyway, that's my presentation for my extra credit. And as you can see, you find the mass along this wire here. Find it through this exact way of getting it instead of the approximate way. And it sometimes can be very simple, or as our squid buddy knows, it can be difficult. Thank you, and happy holidays.